This lecture is about the inverse Laplace transform. We already know how to apply the Laplace transform to a great variety of time domain functions. We also know that we can use it to turn linear differential equations into simpler algebraic equations. If we are able to undo the Laplace transform and go from the S domain back to the time domain, we will be able to solve the associated differential equations. In this lecture, we will introduce the inverse Laplace transform. We will learn how to determine the inverse transform of common S-domain functions. We will introduce the convolution theorem, a very useful result, and we will combine the Laplace transform and its inverse to determine solutions to initial value problems. The inverse Laplace transform. The Laplace transform maps time-domain functions onto S-domain functions. For example, it maps f of t equals 1 to 1 over s. It maps the exponential of a times t to 1 over s minus a. And this is the Laplace transform of sine, and this is the Laplace transform of cosine of 2 times t, and so on and so forth. It is natural to ask whether it is possible for two time-domain functions to share the same Laplace transform. We know that the Laplace transform of f of t is equal to 1 is 1 over s. Are there any other time-domain functions with the same Laplace transform? Define a time-domain function f which is equal to 1 at all times with the exception of just one time instant. Such a function has the same Laplace transform. Likewise, functions which are equal to 1 everywhere but at 2, 3 or generally finitely many points have the same Laplace transform as well. Are there any other functions which are substantially different and have the same Laplace transform? The answer is negative and is given by Lerch's theorem. Lerch's theorem states that if two piecewise continuous time-domain functions f and g have the same Laplace transform, they must be equal almost everywhere, that is, everywhere with the exception of a finite number of points in time. This allows us to define the inverse Laplace transform. If f is a time-domain function with Laplace transform f uppercase, we say that f is an inverse Laplace transform of f uppercase. This is denoted by L calligraphic -1 as shown here. We can now compile a table of the most notable Laplace transforms. For example, 1 has the Laplace transform 1 over s, exponential of a times t has the Laplace transform 1 over s minus a, and so on. Lerch's theorem allows us to swap the columns of this table. This leads to a table of inverse Laplace transforms. For example, the inverse transform of 1 over s is 1. The inverse Laplace transform of 1 over s minus a is the exponential of a times t, and so on. If we want to be very meticulous here, we should say that the inverse Laplace transform of 1 over s is the function f of t equals 1, and all functions that are equal to 1 almost everywhere, but we don't need to be that specific. If an S-domain function is not given in this table, we will need to perform certain manipulations to write it in terms of elementary S functions which have a known inverse Laplace transform. In this example, we have f of s is equal to 2s plus 1 over s squared plus 4. Were it not for plus 1 in the numerator, this would look like the Laplace transform of a cosine. And were it not for 2s, f would look like the Laplace transform of a sine function. What we can do here is that we can split the fraction into a sum of two simpler fractions. The good news is that the inverse Laplace transform inherits the linearity property from the Laplace transform. It is a linear transform. This allows us to apply the inverse Laplace transform on each summoned separately, leading to this time-domain function, which indeed involves the sine and cosine functions. This is a plot of the inverse Laplace transform of f, and this could be the solution of a linear differential equation, for example. We will get back to that later. Next, we will discuss how to determine the inverse Laplace transform in more general cases.